All right, guys, we're going to do an example with negative resonance. So I'm assuming you have watched my initial video of positive resonance because it goes into a little bit more thorough detail about just kind of how to view and explain these steps. So we're going to be a little bit more concise in this one. When we're doing negative resonance, we're going to follow, again, the rule of three. So still usable. And the rule is, again, you count from the atom with a charge on it, atom 1, and you go 1, 2, 3 to the adjacent atoms. You count. If there exists a double or a triple bond between atoms 2 and 3, you can have resonance. And so what you end up seeing happen is this negative charge gets displaced onto the third atom. So let's just do that. We go atom 1, and let's count adjacently, 2, 3. And like, holy crap, we see that there's a double bond between atoms 2 and 3. So we're going to be able to do and perform resonance. So this is fantastic. We're having a great time. We're grinning right now. We're stoked. So I want to explain how this works. And this is different from positive resonance because it's a two-step process. The first step is we drop this charge, or this lone pair is what this is denoting, from the atom onto the bond. And then we go from the next double bond's bond to the atom. So this is extremely important. That first arrow is going atom to bond, and that second arrow is going bond to atom. And this is every step that you do. So if you're trying to draw a resonance structure for a negative charge, you have to follow both of these in order to complete it, because what we know is if you drop down this charge and you do not move up that second bond, you're going to have 5 bonds to carbon. The Holy Grail rules, you can only have 4 bonds to carbon. Like, no way in all of the world are we going to ever break that. We're going to try our hardest to always keep just 4 bonds to carbon. So that's what we have to do. And so we know that it's going to go the charge from atom 1 to atom 3. So if we draw this resonance form, we see that double bond gets moved up, gets moved, and so we see a charge displacement. And this is our next structure. It's important to see that there's no other way we can go with this. We could just go kind of backwards to where we started. So I'm going to redraw, so I'm going to label this resonance form 1, and I'm going to redraw our structure so we don't make it too cluttered. And I'm going to label now, there's this charge. I'm going to say atom 1, atom 2, and atom 3. And what I see again is there now exists a triple bond between atoms 2 and 3. So I can do the exact same thing I just did. So I moved the electrons from atom 1 onto the bond, and then from the bond onto the atom. And so triple bonds, especially alkynes, are extremely confusing because for some reason people try to do the rule of 3, and then for me too, my brain just kind of like breaks, and it's like, all right, what the heck is going on? I get there's carbons there, but my body doesn't want me to draw the arrow there. But we have to make sure that we're going atom to bond, bond to atom, and there exists a carbon right there at that junction. So when we draw this, we see that now between atoms 1 and 2 exists a double bond. Put a dot to signify a carbon. Then we know that this triple bond became a double bond. And then we know there's another carbon coming off of it. But we know that there's a charge right here. And do you see how I broke the linear form? See how it's all linear? There's no angles in any of these carbons. But you see how now I put this going slanted? That's because when the alkyne is no longer present, it doesn't lock you into a rigid linear structure. So this would actually be bent down like we normally would be drawing things, angled and alternating. So we have now our second resonance structure. And again, we're thinking about this. We're like, all right, well, what does this mean? And we have to now put some meaning into this. And the first thing that we do is we identify, well, which one of these is more significant than the other? Is there a major resonance contributor? Right off the bat, I'm looking at this and I'm going, this is the major resonance contributor. And why am I doing that? Well, it's like, yes, all of these resonance structures exist simultaneously all the time in this form. They're constantly, these electrons are constantly moving around, but in one of these positions, there's more of a tendency that it exists that way. And it's more significant because it's more stable, I guess. It's more present at any given moment in time because of the stability. And the stability lies that we have a negative charge. In between these two structures, we have a negative charge on a carbon and a negative charge on an oxygen. Remember on recitation 1, I showed us that Pauling's electronegativity scale? Oxygen is the second most electronegative atom underneath fluorine. So do you think that carbon coming in at, I think, like 2.55 electronegativity, and then oxygen coming in at 3.44, hopefully that's right. Oxygen is significantly more electronegative. So do we think that this charge is going to want to exist on the oxygen or the carbon? And I'm betting $100 million it's going to exist on this oxygen. And because it wants to exist on this oxygen, it's going to be the most stable form. My cat keeps trying to jump up on my table right now, so sorry if my focus is going off. So we can keep that this is the major resonance form because of the elemental stability or the electronegativity preference of this charge on this oxygen. So again, we have these two resonance structures, but what the hell does it mean? Well, let's make some use out of it, and let's draw a resonance hybrid. And again, what I did last time was I draw the most bare bones structure that exists at all times. So I start with drawing just sigma bonds to everything. And then I see what bonds appear and reappear. And I know that this double bond to the oxygen appears at one point. I know that this double bond down here appears at one point. I know that this double bond here appears at one point. I know that this triple bond appears at one point. So I draw a solid line because at any given point there at least is a double bond. So I know that the triple bond appears at one point. And that's the only spots of appearance and reappearance of double bonds in the way that we've denoted this structure. And so the second thing I do is I assign my partial charges. So there exists one here, there exists one here, and there exists one at the end right here on this atom. So this is my resonance hybrid. And again, this looks way cleaner than all of this because this is just confusing, right? It's just a bunch of angled lines, and it might not mean much to us right now. But when we look at this, I'm like, that's pretty clean. And the big thing to keep in mind again is that these dotted lines are the path traveled by the electron highway. And the electron highway drives through the p orbital. So it's an exclusive highway that only electrons can drive. And the p orbital exists at each of these atoms. And between them, the electrons can drive. And the important difference between this structure and the previous example I showed you with positive resonance is now where there's partial negatives, these are hotspot destinations of the electrons. So before with positive resonance, it was spots that the electrons avoided. But in this situation, these are like little restaurants along the electron family vacation highway. And these are like, I guess, Guy Fieri approved restaurants, right? These electrons, they're trying to dine. They really want to dine. But what we notice is that while the electrons like to take dock at these particular 3 points, it likes to dock more often, or the electrons like to eat out more at this restaurant that oxygen hosts because it's the most stable, it's the most secure, it's always going to be open. When we think about reactivity and again chemistry, electrons govern everything. So when we're looking at this molecule and we see that instead of having one dense charge location, it's actually spread out throughout the entirety of the molecule, that's delocalizing this charge. And when we have a delocalized charge, there's stability in this molecule and it's less reactive because you don't have as concentrated of a weapon, and the weapon being electrons to go and grab and react. So resonance and having multiple resonance forms is directly related to being more stable and less reactive. So the big thing to take away from this whole lesson is that when you do draw resonance, you have to draw the arrows correct. So atom to bond and then bond to atom. Every single time. You can follow the rule of 3, but you have to do this arrow manipulation. And then the second is that negative charge differs from positive charge because these are spots that the electrons want to hang out on. And it has the opposite type of interpretation than what positive resonance does, which is spots that electrons are avoiding.